China just pulled off something that the entire semiconductor world said could not be done. Not in this decade. Not without the most advanced chip-making machines on the planet. And definitely not by a company that has been cut off from buying those machines for years. Yet here we are. Huawei, the Chinese tech giant that the US basically tried to freeze out of the global chip supply chain, just announced a new way to build processors. And if the numbers they are showing are real, they are talking about matching chip performance that rivals what 2 nanometers can deliver. Without the machine that makes 2 nanometer chips possible. Without UV. Without ASML. Without any of the tools the rest of the industry depends on. The claim sounds impossible. It kind of is. But here is the part that makes it genuinely fascinating. The idea behind it is not about making transistors smaller at all. It is about doing something that nobody in the mainstream chip industry has seriously attempted at this scale before. And once you understand what it actually is, you will see why engineers around the world are paying very close attention. This video is going to break the whole thing down in plain language. No jargon. No confusing diagrams. Just the real story of what Huawei announced, why it matters, and what it would mean if they actually pull it off. If you find this kind of deep dive useful, it genuinely helps to hit the like button. These videos take a huge amount of research and time to put together, and every like helps more people find them. And if you want to stay ahead on stories like this one, subscribe and hit the bell so you never miss the next video. Alright, let us get into it. The rule that ran the world for about 60 years, the entire technology industry ran on one idea: make things smaller and everything else gets better. Smaller transistors mean faster chips. Faster chips mean better computers. Better computers mean better everything. This idea had a name: Moore's Law. And it worked so well for so long that the whole world just assumed it would keep going forever. Every 2 years or so, engineers would figure out how to shrink transistors again, cram twice as many onto a chip, and performance would jump. Cost would drop, the cycle would repeat. It is honestly one of the most remarkable streaks in the history of human engineering. We went from thousands of transistors on a chip in the 1970s to billions by the 2000s to hundreds of billions today. The chip inside a modern smartphone has more processing power than the supercomputers that filled entire rooms just a few decades ago. But here is the part they do not put on the marketing slides. That streak is slowing down. The gains are getting smaller. The jumps that used to happen every 2 years now take 3 or 4. And the cost of staying on that curve has become almost unbelievable. Building a new leading-edge chip factory today costs somewhere around $20 billion. A single generation of new transistor design can cost $1 billion just in development before you make a single chip. TSMC, the Taiwanese company that makes chips for Apple, Nvidia, and basically everyone else, is fighting for around 6% area improvement with their next generation. 6%. That used to be double-digit. That used to be 50% or more. The easy gains are gone, and the hard ones are getting harder. But for Huawei, the problem is not just that progress is slowing. Their problem is much more specific, and it goes back to a decision made in Washington. The machine they cannot buy. In 2019 and 2020, the US government placed sweeping restrictions on what technology companies could sell to Huawei. The restrictions kept getting tighter. By 2022, Huawei was essentially cut off from the most advanced chip-making equipment in the world. The most important piece of that equipment is a machine called an UV lithography system. It is made by a Dutch company called ASML, and there is basically nothing else like it on Earth. This machine uses a laser to blast tiny droplets of tin, with enough energy to create a plasma that produces extreme ultraviolet light. That light is then bounced through a series of mirrors so precise that even a single atom of contamination would ruin them. And it uses that light to print circuit patterns onto silicon so small that you cannot see them with a regular microscope. Each one of these machines costs around $200 million. They weigh about as much as 2 commercial airplanes. And they are the reason TSMC and Samsung can build chips at 3 nanometers and 2 nanometers today. Huawei cannot buy one. SMIC, the Chinese chipmaker that manufactures Huawei's chips, cannot buy one either. So what do you do when you are cut off from the most important tool in your industry? You get creative. SMIC has been doing something genuinely impressive with older technology. They are using machines called Dove lithography systems, which use a less powerful type of light to print chip patterns. Dove was never designed to make chips as small as what SMIC is now producing. To get around this, they use a technique called multi-patterning, where instead of printing one tiny pattern in a single step, they break it up into several simpler steps, each one printed separately and then combined. It is like drawing a very detailed picture by laying down one color at a time instead of all at once. Through sheer engineering persistence, SMIC managed to push Dove multi-patterning far beyond where most experts thought it could go. They got to what is roughly considered a 7 nanometer equivalent process. That is genuinely impressive. But every extra step in the process adds cost, adds complexity, and adds more chances for something to go wrong. And there is a ceiling on how far you can keep pushing this approach. Huawei knew that. So their engineers started asking a different question. What if transistor size is not the only way to make chips better? The real bottleneck nobody talks about here is something that surprised me when I first learned it. Modern computers are not mostly limited by how fast their transistors can switch. They are increasingly limited by how long it takes information to travel from one part of the chip to another. Think about that for a second. The thinking part is not really the bottleneck anymore. The moving information around part is. Huawei says that in modern computing systems, more than 80% of energy can be spent just moving data around, not actually computing anything. 80%. That is not a typo. The chip is spending most of its energy playing messenger, not doing math. To understand why, you need to think about what a chip actually looks like on the inside. Imagine a city. A very, very small city with hundreds of billions of tiny workers packed into an area smaller than your fingernail. These workers are the transistors. They do the actual computing. But they are connected by a network of tiny metal roads, wires really, that stretch across more than 20 layers inside the chip. Every time information moves through one of those wires, 2 things slow it down. First, the wire resists the flow of electrical signals, kind of like how a narrow pipe slows down water. Second, the wire acts a little bit like a tiny battery that has to charge up and then drain every single time a signal passes through. Engineers call this arc delay, and the longer the wire, the worse both of these effects get. This is actually the main reason why the clock speeds in your computer processor have barely changed in about 15 years. We are not limited by how fast the transistors can go. We are limited by how fast the signals can travel between them. So here is the insight that changes everything. If the problem is distance, what if you could just make the distances shorter? Not by shrinking the transistors, but by rearranging where they sit relative to each other. What if instead of spreading a chip out flat like a city on a plane, you stacked parts of it on top of each other like a skyscraper? Folding the chip in half. This is the core of what Huawei announced. They call it tau scaling, and the name comes from the idea that they are optimizing for time, specifically the time it takes for signals to travel through the chip. The concept is actually pretty easy to picture. Take a piece of paper covered in text. The words at the top left are far from the words at the bottom right. Now fold the paper in half. Words that were centimeters apart are now right next to each other, separated only by the thickness of the paper. Huawei wants to do that with a chip. Take a processor that would normally be laid out flat, divide the logic up, and fold one half on top of the other. Things that used to send signals across several millimeters of flat silicon now only have to send them a tiny fraction of that distance vertically. Millimeters become microns. The journey shrinks by a factor of 1,000. And when the journey shrinks, so does the delay, the energy, and the heat generated by all that data movement. In their early results, Huawei reported a transistor density of 238 million transistors per square millimeter using this folded approach. That is about 55% more logic packed into the same footprint compared to their flat design. And they are claiming that on a roadmap out to around 2031. This approach could deliver performance equivalent to what you would expect from a 1.4 nanometer chip, all without ever needing UV lithography. Now, before you get too excited, there is a very important thing to understand about that 1.4 nanometer claim, and it is something a lot of the headlines about this story got wrong. When chip companies talk about nanometer numbers today, those numbers are more of a marketing label than a physical measurement. 2 nanometer does not mean transistors are literally 2 nanometers wide. The number is shorthand for a level of performance and density. What Huawei is saying is not that they have invented a new type of transistor that is 1.4 nanometers in size. They are saying that by stacking 2 layers of their existing chips on top of each other, they can fit enough transistors into a given area to compete with what a chip described as 1.4 nanometer could do. That is still impressive, but it is a different kind of impressive. Stacking 2 mature processes does not create a new manufacturing process. It is more like a system-level trick than a transistor-level breakthrough. The real breakthrough, if they can actually deliver it, is something else entirely. The number that has engineers nervous when Huawei presented their plan, one specific number caught the attention of every semiconductor engineer who saw it. Not 1.4 nanometers. The other number, 1.5 microns. This is the bonding pitch Huawei is targeting for connecting their stacked chip layers. Here is why that matters. When you stack 2 chips on top of each other, those 2 layers have to communicate. Constantly, billions of times per second. The connections between them are tiny copper dots that bond directly from one layer to the other. The smaller those dots and the closer together they are, the more connections you can fit, and the faster information can move between layers. The spacing between those connection dots is called the bonding pitch. And today, the best in the world is around 9 microns. That is what AMD uses in their 3D V-cache memory stacking. TSMC and Intel are in roughly the same range. Huawei is talking about 1.5 microns. That is 6 times smaller than the current best. 6 times more connections per unit of area. And here is what makes that claim so striking. To go from 9 microns to 1.5 microns is not a small step. It requires new equipment, new materials, new processes, and new ways of testing whether the bond actually worked. It is the kind of leap that the industry usually takes a decade to achieve one small step at a time. If Huawei pulls it off, it changes the math on everything. With enough connections between layers, the 2 stacked chips stop behaving like 2 separate chips and start behaving like one single, unified, extremely dense processor. The seam between them disappears from a performance standpoint. That is the vision. But then you hit a wall. a hot wall. The problem that could stop everything here is the part of this story where physics shows up and ruins the party. Memory chips run cool. They sit relatively quietly and just hold data. Logic chips do not do that. Logic chips switch billions of times per second, and every single switch generates a tiny bit of heat. Spread that across hundreds of billions of transistors running at full speed, and you get a chip that gets very, very hot, very fast. Right now, that heat escapes mostly from the top and bottom of the chip, through a heat spreader into a cooling system. In a data center, that cooling system can be enormous. Liquid pipes, giant fans, entire buildings designed around moving heat away from processors. In that environment, a hot chip is manageable. Huawei's first target for this technology is not a data center chip. It is a Kirin processor, a smartphone chip. Your phone has no fans, no liquid cooling, no room for any of that. It has a thin slice of metal and maybe a small graphite sheet to move heat around. And it sits in your hand, so it cannot even get very hot or it would hurt you. When you stack one hot logic chip on top of another hot logic chip, the heat from the bottom layer has nowhere easy to go. The top layer is sitting right on top of it, trapping it. You have essentially built a tiny heat sandwich, and the filling is on fire. This is not a small engineering challenge. It is genuinely one of the hardest problems in the physical world right now. Some research teams are exploring materials that conduct heat better, or microchannels built into the silicon itself that carry cooling fluid directly through the chip layers. But none of those solutions are proven at mass production scale yet. Whether Huawei has a credible answer to the heat problem is the question that determines whether tau scaling is a real roadmap or a very impressive sounding presentation. If they solve it, the roadmap looks extraordinary. If they do not, the stacked logic idea runs into a ceiling before it ever reaches its potential. That is not a criticism. It is just the honest shape of where things stand. The announcement is real. The engineering challenges are real. And the outcome is genuinely unknown. What this actually means, let us zoom out for a second and ask the bigger question. Even if everything works, what does tau scaling actually change? Moore's law was special because it made chips better and cheaper at the same time. Every generation, you got more performance and you paid less per transistor. That is an almost magical combination. It is what put computers in every pocket on Earth. Tau scaling does not do that. Stacking chips is more expensive than not stacking chips. You need more precise manufacturing, more steps, more testing. The bonding process at 1.5 microns is going to cost more than the bonding process at 9 microns. So what you are trading is cost for performance. You get more capability in the same footprint, but you pay more for it. That is still valuable. In a world where traditional scaling has slowed down, any path to more performance matters. But it is a different kind of progress than what the industry ran on for 60 years. The other thing worth noting is that Huawei is not alone in thinking about chips this way. AMD already stacks memory on logic in their processors. High bandwidth memory stacks 12 memory dies on top of each other. Intel and TSMC both have their own three-dimensional packaging roadmaps. And deep inside research labs, engineers are building transistors that stack vertically on top of each other at the atomic level. The industry was already moving in this direction. What Huawei is doing is pushing it harder and faster than anyone else, partly out of necessity, and partly because they have the engineering talent to try. The 1.5 micron bonding pitch, if they achieve it, would be a genuine world first. The heat problem is real, but not impossible. And the density numbers they are already showing from early implementations are not fake. They are just not the same thing as having a true 1.4 nanometer process. They are something different. Something that fits in a category we do not really have a clean name for yet. Maybe the most honest way to say it is this. Huawei found a door in a wall that everyone else assumed was solid. Whether that door leads where they think it does is something we will find out over the next few years. What comes next? Huawei's roadmap puts the full realization of tau scaling at around 2031. That is 5 years away. A lot can change in 5 years in this industry. What to watch in the near term is whether SMIC can actually manufacture the bonded chips at scale and with good yields. Yield means how many of the chips you make actually work properly. In advanced manufacturing, getting yield right is often harder than getting the design right. A chip that works beautifully in a lab but fails 60% of the time in production is not a product. The thermal story is the other one to track, as more details come out about how Huawei plans to handle heat in a stacked Kirin chip. That will be the clearest signal of whether this is really production-ready thinking or still an aspirational roadmap. And then there is the broader question of what happens to the rest of the industry if this works. If 1.5 micron bonding becomes real and manufacturable, other companies will want it too. TSMC and Intel will accelerate their own three-dimensional packaging programs. The race will not be over. It will just move to a new arena. That is kind of the beautiful and maddening thing about semiconductor engineering. Every time someone says it cannot be done, someone else goes and does a version of it. Not always in the way the skeptics imagined, not always on the timeline they promised, but eventually. Huawei's announcement is not proof that they have already won. It is proof that they are playing. And in a game this important, being a serious player is not nothing. That is the full story of what Huawei announced and why the semiconductor world is paying attention. If you made it this far, drop a like on the video. It genuinely helps this channel reach more people who are curious about how technology actually works. Subscribe and hit the bell so you catch the next deep dive when it drops. And I want to know what you think. Do you believe Huawei can actually solve the heat problem and make this work in a real smartphone? Let me know in the comments.